Observe three mutually gravitating bodies in a void. Their paths tangle, violently diverge, and trace chaotic, looping trajectories. For over 300 years, predicting the exact long-term trajectories of a three-body system like this has proven mathematically impossible via analytical integration. From the era of Isaac Newton to the work of Henri Poincaré, this analytical failure has remained a defining deadlock in classical mechanics. The mathematical breakdown occurs because standard physics treats these bodies as infinitesimally small point masses. These point dynamics generate an extreme sensitivity to initial conditions, where the tiniest measurement discrepancy rapidly cascades into wild, unpredictable movements. This resulting deterministic chaos relies on a specific structural assumption, the idea that space itself is a passive, empty geometric stage. Modeling the universe as a void suggests that chaos is an inherent physical reality. However, this may instead be a mathematical artifact of an incomplete model. This differential equation governs point masses in a vacuum. The highlighted denominator represents spatial distance. Gravity must operate across empty space without a physical mediating medium. Without this medium, inverse square interactions create runaway feedback loops as bodies draw closer together. Because the classical framework lacks mechanical stress mediation, it possesses no physical way to dampen or constrain these nonlinear interactions, which leads directly to deterministic chaos. The elastic continuum theory proposes a different starting point. Space is not empty, but a dense, hyperelastic solid known as the plenum. In this model, celestial bodies are no longer treated as isolated points separate from the space they occupy. They are instead defined as topological macrosolitons, governed by the vector Georgiades master equation. A macrosoliton is a localized topological knot, a physical deformation permanently embedded within the continuous elastic lattice of the vacuum. Under this framework, matter and space are a single continuum. Celestial bodies are simply mobile nodes physically woven into the fabric of space. Equation 2 demonstrates how multiple solitons interact. Each node generates a localized volumetric deformation field that radiates outward into the lattice. These bodies do not rely on distance-based forces. Instead, their individual deformation fields undergo a nonlinear superposition within the shared elastic lattice, represented here as U total. These independent strain fields expand and merge into a single continuous global strain energy gradient. This collective state is defined as the global strain energy density of the interconnected lattice. Orbital mechanics then becomes a search for the minimum energy dissipation path through this shifting global strain field. Equation 3 defines the stabilized wave coupling modes of this system. We begin with the shear moduli tensor,Cijkl, which represents the structural stiffness of the medium. Because this tensor establishes that the vacuum has finite stiffness, the medium itself inherently resists deformation. On the other side of the equation, the Sine-Gordon potential term defines the limits of that deformation. This potential establishes bounded restoring forces within the lattice, which mathematically prevents trajectories from diverging towards infinity. The combined effect is an elastic back reaction, where the medium physically pushes back against the movement of the solitons. This physical pushback functions as a mechanical governor. It introduces the damping parameters required to constrain the nonlinear interactions that lead to divergence in the Newtonian model. By integrating these restoring forces, the multi-body system is transformed from an unconstrained network of points into a stable continuum resonator. This split-screen comparison shows the difference between the two frameworks. On the left, standard Newtonian integration. On the right, solitons within the elastic plenum. Without the back reaction of a physical medium, the Newtonian trajectories inevitably devolve into unpredictable diverging loops. But on the right, the physical constraints of the solid vacuum force the trajectories to relax into synchronized patterns. The erratic behavior is damped by the overlapping strain fields, which guide the bodies along stable paths. Under these conditions, the erratic trajectories resolve into predictable paths. The bodies effectively function as a single interconnected system, locked into a stable wave coupling mode. The three-body problem is regularized by moving away from the concept of action at a distance. Treating celestial bodies as topological solitons in a shared substrate provides a physical basis for orbital stability. The deadlock of the point mass model is addressed by accounting for the mechanical properties of the medium. The interaction is no longer an unconstrained calculation, but a bounded wave interaction. The elastic continuum theory reduces multi-body orbital mechanics from an unsolvable point mass puzzle to a deterministic continuum interaction.